Okay, so welcome back, everybody. So, uh, the thing that we want to talk about today, that now we have the little um, kind of foundational stuff taken care of in the form of divergence and curl. Well, maybe I'll say like one more thing about divergence and curl before we move on. Um, oh, do I want to include? I might include. I think I'll include that a little bit later. Uh, so yeah, I will return to divergence and curl later toward the end of chapter 15. But there's also something else I wanted to say about it that I could say now, but I'll wait until we return later. So I think I'll go ahead and start on the next topic, which is the topic of line integrals. Now, line integrals kind of misnamed in a sense because um, you might think that a line integral is an integral along a line, uh, and that's kind of true, and it can be true, but it's really kind of a better name for these would be curve integrals. Um, because that's what they are. So, what is the idea behind a line integral? If I return to Calc 1 land and I have an interval AB. Okay, here's my interval AB, and on that interval I have, say, the graph of this function. Okay, then if I am, say, wanting to find the area under the graph of that function on this interval AB, we have no problem saying that I am integrating along the interval AB, right? So I integrate along this interval. Okay, that's the terminology we use. So what if I take that interval, right, and I consider it, right? It's a line segment, right? It's a piece of a line. So intuitively, I'm integrating along this line segment, but it's a particularly simple one, right? So what if I took this and I changed it a little bit? Maybe I stretched it out, so it's still a line, but it's maybe stretched out a little bit, and I want to think about the notion of integrating along this thing. Okay. Well, I can do that. But let's say that I got a little bit crazier and I maybe took this same thing that I want to integrate along, right, in the same style, and I kind of shook it up. If I thought of this as a string, I like did this to it. I wiggled it around so that the thing I'm integrating along looks more like this now, right? Okay. And again, we're still not totally happy with this, although, now we're definitely doing something different than we were before here. We're integrating along a thing that looks like this, but let's keep going. Instead of doing this, I take my piece of string and I maybe arrange it into some curve that even looks like this. Okay. Now, of course, the difference between this and this is while I can view this as a graph of a function in the usual way, this I can't. I would require a parameterization, right, R of t, to describe this thing. And so, what is it that I'm doing in a line integral? I am integrating along a parameterized curve. Okay. And I've drawn this, of course, in the plane because that's easier to draw, but the idea is to integrate along a parameterized curve in space. Okay, I can do this in the plane, and in fact, we're going to have a named theorem that is going to rely on us doing this in the plane. But if we can define it in space, then the definition is going to be the exact same thing in the plane. We're just going to drop the z coordinate, right? Okay. So this is really what we're doing, and that's why I say it should be called a curve integral, because really what you're doing is you're integrating along a curve. Okay, so that's what a line integral is. Now, we're going to have two notions of line integrals. The first one is, so two notions of line integrals. And these are split by what kind of thing you're integrating. So two notions of line integrals. So the first is integrating a function, say f of xyz, along a curve C in space. And the second one, which is actually the thing that we're interested in, we are basically only defining the first one because we're required to do that to make sense of the second one. So the second one is actually the thing we're interested in, and that is integrating a vector field big F of xyz along a curve C in space. This is the one we're interested in, okay? But we have to define the first one to make sense of the second one. Okay, so this is a little bit different, and it's actually the reason why you might wonder, like, why did we start out talking about vector fields in 15.1, right? What was the deal with beginning our discussion of this last chapter with vector fields? It's because these integrals that we're going to be computing involve the integration of a vector field. So we'll make sense of that here in a little bit. Okay, so let's define this first thing. So to define the first notion, let's draw a picture of space here. So here's representation of space. Here's my typical space curve drawn like this. And we'll say my space curve has endpoints like that. Okay. So let's look at this space curve. Let's define this thing as having the parameterization as usual, like we used to do back in chapter 12. So the curve C, say, has a smooth parameterization R of t in the usual way. So this is x of t I plus y of t j plus z of t k for t in the closed interval AB. Okay. All right. So once we have done that, if I have a function, right, so this is space as normal, and on some region in space, it makes sense to talk about a function, little f of xyz, then the integral over C of little f of xyz ds, this is called the line element. Okay, don't focus too much on this because this is really just notation. In the same way that you don't actually do anything with the, say, dx or dy or dt that shows up in a normal integral in Calc 1. You don't actually do anything with that. That is just kind of telling you the variable you're integrating with respect to, right? Or if you view, the integral as coming from this limit of Riemann integral type things, then the d thing under the integral comes from the delta thing you're taking the limit of, right? And the reason for that is because to actually go into a description of why this d thing is underneath the integral, it requires a lot of advanced math stuff that technically it's just really annoying to have to explain. It would take a bunch of background, but the quick answer, this is going to confuse everyone, but I'm going to say it anyway, is that you actually can't integrate a function. You can only integrate what's called a form. So you can integrate what are called differential forms. Integrating a function actually doesn't make any sense. And you're going to be like, what are you saying? But that's how it is. Unfortunately, this is something that you can't actually talk about until you're in very complicated and much more advanced math classes. So anyway, I'll stop saying anything now. Okay. So anyway, this is what I write here, just part of the notation. This integral over c can be computed. This is our definition of a line integral for a function of 3 variables over my curve c. This is the integral from a to b of my function f with the parameterization for r plugged in. Okay, times the length dr dt. I ran out of room here. I'm going to rewrite this actually. Okay, so I'm going to rewrite this because I ran out of room. So my line integral for a function f of x, y, z ds, this is defined to be the integral from a to b. A to b is the window of this parameterization, this curve c. Okay, so here's my curve c. This parameterization is defined for t in that window, a to b. And so this is the integral from a to b of f with the parameterization plugged in. So f of x of t, y of t, z of t times the length of dr dt. That's this derivative of the parameterization. Okay, dt. So notice this is just a Calc 1 integral. It is an integral with respect to t of this quantity. So even though this is a function of 3 variables, once I plug the parameterization in and multiply it by the length of dr dt, this is now a giant, this integrand is just a function of t. And so I'm integrating that function of t with respect to t. This is a Calc 1 style integral. Okay, so once you know this definition, once you write this out, this is an integral that you could have done back in Calc 1. Okay, nothing special here. There's no multiple integrals or anything like that. All right, so here's my definition. This is the line integral of a function. Okay, so this is line integral along curve C of a function f of x, y, z. So that's how we say that. All right, so before I move on to an example of this really quickly, one question you might have is, what is this computing? Right, so if I go back to the thing that kind of spurred me to start talking about this, right, when I compute the integral along the interval AB, I'm computing an area right under this curve. The problem is the second you move to a parameterized curve, now there is no like function over that curve, right? Because the function in question is a function of 3 variables, I can't even plot it, right? I can't even graph this thing. So what is it that is being computed here? Well, one example, so here's an application. Suppose we have a metal wire, right? A thin metal wire. And I take that metal wire and I shake it up and I stick its 2 ends somewhere in space, but it is tracing out some trajectory in space. So we have a metal wire that sits along the curve C in space. Okay. And suppose, right, this metal wire is not necessarily uniform, but I have this metal wire C in space, and I have the mass density function for that wire. So let's suppose that f of xyz is the mass density function for that wire. Then the mass m of the wire is equal to the line integral over c of the mass density function of the wire. Okay, so this is one application. This isn't the only physical thing that you can ascribe to it, but this is probably the most straightforward one. Okay. All right, so let's do a quick example here of a line integral. And let's do a line integral on an honest-to-God line, because that's somehow pleasing to us, right? That we are doing this for an actual line. We're living up to the name. So let's see be the line segment in space from, say, 0, 0, 0 to 1 minus 3, 2. Okay. And I want to compute the line integral over that c of x plus y squared minus 2z ds. Okay. So before we can begin, we need to parameterize c. So we have a line segment from the origin, 0, 0, 0, to 1 minus 3, 2. We weren't given the parameterization exactly, but we can find it pretty easily from that. How do I parameterize the line segment from 0, 0, 0 to 1 minus 3, 2? Well, you might remember that the way that we wrote out the equation for a line in space was actually a parameter, well, in parametric form, right? Not in symmetric form, but the equation for a line in space in parametric form was a parameterization of that line thought of as a curve, right? And here it's easy to see that this parameterization would be t I minus 3t j plus 2t k for t between 0 and 1. All right, this will do it. This is not the only possible way that you could parameterize this curve C, but this will get the job done. All right, and so what pieces do I need in order to compute a line integral? So I need the function that I'm integrating over. Well, I have that. That's my integrand. I need to plug that into the parameterization into the integrand. So I need the parameterization for C, which means I need the window the parameterization lives in. So I have that. I have the parameterization. I'll do all that algebra in a second. I need to compute dr dt and the length of dr dt. Okay, and so let's do that. What is dr dt here? So dr dt, I'm just going to go slot by slot here. This is I, right, minus 3j plus 2k. Oh, well, that's pretty easy. Okay, and so the length of dr dt is square root of 1 squared plus minus 3 squared plus 2 squared. Right. So this is like the square root of 1 plus 9 plus 4, so 14. Okay. All right. And so, how do I do this integral? So this would be the integral over c of x plus y squared minus 2z ds. This is equal to the integral from 0 to 1 of plugging in x of t is t here. So this is t plus plugging in y is minus 3t. So this is plus minus 3t squared. right, minus 2, plugging in the parameterization for z here, this is 2t, okay, and that is multiplied by the length of dr dt, so that's multiplied by square root of 14 dt. Okay, so let's do this algebra real quick. So I can pull the square root of 14 out, and this is the integral from 0 to 1 of, let's see here. So here I have t, here I have another t term, and here I am going to have a t squared term. So let's think for a second. I have t minus 4t, so that's minus 3t. Plus minus 3t all squared is 9t squared. Okay, and so that's an integral. It's not too tricky to do here. So this is square root of 14 times, just doing this term by term here. So minus 3t, if I integrate that, I get minus 3 halves t squared. Integrating 9t squared, I would get 9 over 3t cubed, so I get 3t cubed, and all of that is evaluated from 0 to 1. Every term has a t in it, so plugging in 0 yields 0, so I only need to plug in 1 here. So plugging in 1, I get minus 3 halves plus 3 here, and so I get 3 halves times square root of 14. And that is my line integral. Okay. All right, let's do one more example. So let's say, let C be the twisted cubic we first talked about way back in chapter 12. So let C be the following curve with parameterization r of t, which is ti plus t squared j plus t cubed k. For t between, we'll say 0 and 2, or 0 and 1/2. All right, so there's C. Let's find the line integral over C of the function 8x plus 36z ds. Okay. All right, so again, we have the parameterization already. I don't need to even come up with it. I need to compute dr dt and the length of dr dt, and then I need to apply that to my definition here. Okay, and so what is dr dt? So dr dt is I plus 2tj plus 3t squared k. And so the length of dr dt is equal to square root of 1 squared plus 2t squared plus 3t squared squared. And so this is square root of 1 plus 4t squared plus 9t to the 4th. Right. All right. Cool. So now we're ready to roll here. So the line integral along my curve C of 8x plus 36z ds is equal to the integral from 0 to 1/2 of, I'm now plugging in the parameterization here into this function. So this is 8 times x of t, right? And if we're viewing our parameterization as x of t I plus y of t j plus z of t k, right? These are my component functions as usual. This is 8t plus 36 times z here, which is what? This is 36 times t cubed. Okay, times the square root of 1 plus 4t squared plus 9t to the fourth dt. So now you see it was a rather judicious choice of integrand function here that gave us what? Well, it gave us exactly what we need in order to integrate this nasty radical expression here, right? Normally when you have something like this showing up underneath an integral sign, it's bad news, but we have exactly what we need here to do a very simple substitution integral, right? So if we take u to be the thing underneath the radical, right, what is our du? Our du is exactly 8t plus 36t cubed. Boom, right? That's exactly what we have there, so that's nice. All right, so using substitution really quickly, this is going to be, this is going to be u to the 1/2 du, right? And so the integral of u to the 1/2 du is u to the 3/2 over 3/2, so that's 2/3, right? Times 1 plus 4t squared plus 9t to the fourth to the 3/2. Okay, evaluated from 0 to 1/2. Okay, and so what is this? This is 2/3 times, well, first I have the expression where I've plugged in 1/2 here, so this is 1 plus 4 times 1/2 squared, so that's 1/4, plus 9/16, all right, so 9 times 1 over 16, okay, to the 3/2, right, minus 1 plus 0, plugging in 0 here, plus 0, so that's 1 to the 3/2. Okay, and this is good enough for now. All right, this expression is fine. I'm not going to make that too much nicer because nothing here works out to be a perfect square or anything, so this is going to be a nasty thing. So the one thing I can say is that's 1, and this is going to be some expression that I could make look nicer, but I'm not even going to bother. Okay, so that's my line integral. Okay, now of course we are not done with our understanding of line integrals because this was only our first notion, right? This was the notion of a line integral of a function over a curve C. And so a couple of things I want to talk about are more conceptual. So one, note, if I have a C, right, a curve C that has parameterization as usual, I'm not even going to write it out, and I integrate the function 1 over C ds, what do I get? This is the integral from a to b, which is where my parameterization lives, of 1 times the length of dr dt dt. Or this is the integral from a to b of the length of dr dt dt. What is that? You've computed exactly that integral before. Now what is that? Going back to chapter 12. for a second. What is this quantity? Right, this is a quantity you might be asked to take an integral of when you're taking your final exam. Right, this is an integral you might have to do for that early chapter 12 material. Right, because this is the integral you compute when you compute the length, right, of the curve. Right, so this is the length of C. So you can view this length of the curve, right, as a line integral, okay, over C. So, you know, if you're trying to develop a notion of integrating along a curve, seeing something like this tells you very much that you're on the right track, right, that your definition is the right one, because it, you know, specializes to this case to give you something really nice, right? So you really are integrating along the curve in some sense. You're computing the same sorts of quantities, lengths and areas and stuff, doing this line integral. So this is good. This is kind of more evidence that our notion of line integral is correct. One other thing I wanted to mention that's actually important. It was kind of a side case when we talked about stuff like this before, but it's actually important for us in this section. And that's, what if my curve is piecewise? So let's see that this is a piecewise smooth curve. So let's say, for instance, you know, here's an example of my curve. So there is the piece C1, and here is the piece C2, and here is the piece C3. Okay, so this is my curve C, right? My curve C is made up of those three pieces. So first I go here, then here, then here. Okay, and we'll say that those intervals that define these in question, so you know, these intervals in question are, you know, like A1, B1, A2, B2, and A3, B3, right? I'm actually not even going to write that out. What if I wanted to do a line integral over C of some function? Right? Well, you might guess that the way that integrals typically work, right, is that you can split them over objects like this, and that is in fact the case. In fact, this line integral can be computed as the sum of the line integral done in pieces, right, plus the line integral over the piece C2, f of x, y, z, ds, plus line integral over the piece C3 of the same integrand function. Now, this would be three separate integrals you had to compute in this case, or if this thing were split into more pieces, there would be more integrals you'd have to compute, and there's nothing special about splitting it into three pieces, so of course you could generalize this to any n you like, but here's the picture I drew. So technically this splitting works for any number of pieces of this piecewise curve that you have. Okay. The reason why this is more important for us in this chapter is because we are indeed going to encounter a lot of curves that are piecewise like this, and we're not going to be able to get away from it. We are going to have to deal with the fact that we're dealing with, say, some 2D region in the plane, and its boundary is some piecewise smooth curve that looks like this. Okay, so think of like a semicircular disc or something. It's going to have corners. All right. So that's the idea here, and we'll see specific examples of where and how we have to deal with this later. Okay, so let's see. Now I think is a good enough time to discuss line integrals over vector field, or of vector fields over a curve. Okay. So this is our second notion and our more important notion, because this is actually what we're interested in. All right, and so we're actually more interested when integrating vector fields over curves. All right. Okay. So how is this done? So let's say we have the exact same scenario. So let big F of XYZ be a vector field. Okay, and it's a vector field that is nice enough on the curve itself, right? So nice enough on C itself. Okay, where C is a smooth curve, or a curve with smooth parameterization in the usual sense. So R of t is x of ti plus y of tj plus z of tk. All right. For t living in some interval a to b. Okay. So, how do I discuss the vector field, or the integral of the vector field along this curve C? So the line integral of the vector field F along C is this first expression I'm going to write is purely notation, but it's notation that helps you remember how this is done. So this is the integral over C of my vector field F. And I write this with the notation, the integral over C of my vector field F dot dr. This is purely notation, but it's good notation because it helps you remember how this goes. The way this is defined is that this is the integral over, or from A to B, of my vector field F with my parameterization plugged in, dotted with dr dt. Okay, and that is the thing that I integrate dt. Couple things to note. Okay, so first thing to note, this is similar to what I was doing before when this was a function instead of a vector field, but here, so I'm plugging in my parameterization into my vector field, but that gives me a vector, right? That gives, for some particular point along the parameterization, that gives me a vector. And I don't really know what it means to integrate a vector. Okay, and so when I compute dr dt, of course, I also get another vector. And so if I'm going to multiply by some dr dt, right, compare what we did for a function. We didn't multiply by dr dt, we multiplied by the length of dr dt. Right? So we multiplied by, bring it back for a second. So when we're doing it for a function, we multiply by the length of dr dt, which is a scalar valued thing. The function itself is a scalar valued thing, so I just have a scalar valued thing under the integral, which is totally fine. Right? That's the expected thing. But here I have vector, right? And I don't know what it means to integrate that. I have another vector here, dr dt, not the length of dr dt. This length of dr dt basically is the term that gets canceled out when you consider the special case of a function instead of a vector field here. Okay, but I'm not going to go through that derivation. Just take this, completely for granted as the definition of the line integral of a vector field. So we have vector and vector, but when we dot them, we get a scalar valued thing. So this is still, on the right-hand side, a Calc 1 integral. right? So this is still an integral in the sense of Calc 1. So once you understand how to compute this dot product, you end up with some function of only t, a single variable, and so computing this integral is still something that you could have done back in Calc 1. Okay, so that's the first thing I wanted to note. Second thing I wanted to note is, trivially, I'm not taking the length of dr dt and putting it underneath the integral now. I'm taking dr dt itself. How does this change things? Well, if you remember back when we talked about curves, right, that were parameterized, and a notion of orientation on a curve, right? So when I have a point on a curve and I think about maybe a particle traversing this trajectory, right, this curve needs an orientation assigned to it, right? So for a curve, there's only two directions, really. So an orientation we can just think of as a specified direction that is our positive direction on the curve. So maybe we think about a curve being oriented. So this curve, we think about it being oriented so that it is clockwise, right? So maybe like this, okay, is my direction around the curve. But how do you read off the orientation of a curve if you know its parameterization? Do you remember how we did this? So way back in ancient times, I told you that when it comes to orientation concerns, if you actually have the parameterization for the curve in front of you, that encodes the orientation in it. Okay, and the orientation that it encodes in it is the direction the tangent vector is pointing. Right? So it's the direction the tangent vector is pointing. And so, if this is a curve that has this orientation that I've specified, when we compute the tangent vector at that point, or at any point, the tangent vector should be pointing in this direction. Okay. So if we have a parameterization that is implicitly giving us an orientation, that is a direction, right? A specified direction along the curve. Okay. Now, what is the thing you notice about this versus what we had before? So let me put them side by side here. Well, forgetting about the differences between these two things being vector valued, so we have to dot them to get some scalar valued thing, and I didn't have to do that here. Okay, one thing you notice is that because I'm taking the length of dr dt here, and dr dt is not showing up anywhere else in this, the orientation actually didn't matter here. So orientation didn't matter. Orientation didn't matter at all. What's another way to see this? Well, we actually did an example. Let me see if I still have it. There we go. So I described C in the example we did as a line segment from 0, 0, 0 to 1, minus 3, 2. Now that specifies a direction and orientation. The question is, would this computation have been altered in any way if I had oriented it backwards? So what if I had oriented it as the line segment from 1 minus 3, 2 to 0, 0, 0? Would it have changed what came later? Well, no, right? The dr dt I would have computed, and it would have changed the sign of r of t. So if I wanted to parameterize going the opposite direction, I could have flipped the signs here, if you like. But when I actually compute this length, of course, I'm still going to get square root of 14, and that's the only thing that it contributes to this integral. And so the orientation wouldn't have mattered. I could have said, let C be the line segment from 1 minus 3, 2 to 0, 0, 0, which is the same curve oriented in the opposite direction. Okay, so I could have let it go from 1 minus 3, 2 to 0, 0, 0. Same curve oriented in opposite direction. And it wouldn't have mattered because I would have still gotten the length of dr dt as square root of 14, and I would have proceeded in the exact same way. Okay, And you can try that with other curves if you like, that the orientation didn't matter in that case. All right, but the orientation matters here. Okay, so big note, orientation matters, and we'll talk about that in a second. Okay. And if I don't get a chance to mention or to talk about it today, then I'll mention it tomorrow. So orientation matters. Okay, this will be particularly important because we can actually use it to our advantage sometimes. The fact that orientation matters. Okay, so first of all, before I do, I'll probably only have time for a single example, but what does this mean, right? I gave a physical interpretation of what it meant to integrate a function over a curve. What does it mean to integrate a vector field over a curve? Well, here's an example. If my vector field F is force on an object moving along a curve C, so if F is force on an object moving along a curve C in the direction of the orientation of C, or in the, let's say, in the direction of motion. So the curve C, we should say, is oriented in the direction of motion. So C is oriented in the direction of motion here. It matters, okay? It matters that C is oriented in the direction of motion here, or else what I'm going to say is not going to be true. So that's one of the consequences of orientation mattering for this thing. But if F is a force on an object moving along curve C, oriented in the direction of motion, then the line integral along C of the vector field F is W, which is the work done by the force on the object as it traverses this curve. This is the work done by the force. F on the object as it traverses C. Okay. So even though these things that we are computing, right, don't have the nice visualization that you got when doing some more typical kind of integral, you're still computing something that's important and has plenty of applications. All right. So let's do a quick example. So let's do an example, and we'll even phrase it in physics terms here, right? We'll say a particle moves upward along the circular helix C parameterized we'll parameterize it so that it is moving upwards here. That's the normal parameterization. That is R of t is cosine ti plus sine tj plus tk for t between 0 and 2 pi, so one arc of this circular helix. Under a force given by the vector field big F of xyz is minus zyi plus zxj plus xy k. Find the work, W, done on the particle by the force. All right. So we know from what I just said that this work is to be computed via a line integral. All right, so how do I do this? Well, as before, I need my parameterization, have it. I need to plug my parameterization into my vector field and dot it with dr dt. Well, I'll do that algebra in a second, but I need to compute dr dt first. All right, so let's compute dr dt before I can go on. So dr dt here is minus sine ti plus cosine tj plus 1k. Right? So then how do I compute this work? So this work is computed by this line integral over c of f dot dr, which I compute from my definition as the integral from 0 to 2 pi of my big F vector field with x of t, y of t, z of t plugged in, dotted with dr dt, dt. Right. So let's plug this parameterization into F and dot it with dr dt, right? So here's F, here's R. I plug R into F, dot it with dr dt. Okay, so let's do that. I need to write this on a new sheet. So this is equal to the integral from 0 to 2 pi of, first I have my vector field F with the parameterization cosine t sine t plugged in for x, y, and z. Okay, and so what do I get when I do that? So F is minus zy, zx, xy. Right? So this is going to be minus t sine t plus t cosine t plus cosine t sine t, right, is going to be my F with that parameterization plugged in. So writing that out, this is minus t sine t I plus t cosine t j plus cosine t sine t k. And that vector is dotted with dr dt, which I found to be minus sine t cosine t 1. Right, so this is minus sine ti plus cosine tj plus 1k. And whatever I get out of that, I get some scalar valued thing in terms of t, and I integrate that with respect to t. Okay, so when I work through this and simplify, what do I get? I have the integral from 0 to 2 pi of, here I'm going to have plus t sine t squared. So that's t sine t squared. So this is t sine squared t plus t cosine squared t. Okay, plus cosine t sine t times 1. And I integrate that with respect to t. Now again, I don't go ahead and start doing this because here I can make this much simpler by recognizing the Pythagorean identity. Cosine squared t plus sine squared t is 1, so this is just t cosine t sine t. So this is the integral from 0 to 2 pi of t plus cosine t sine t dt. So then what do I have here? Integrating term by term here. So its first integral is 1/2 t squared plus, doing the second integral, I can do this with a substitution. So if I let u equal sine t, then du is cosine t dt. So this is sine squared t over 2. So this is 1/2 sine squared t, and that's all evaluated from 0 to 2 pi. Plugging in 0, I get 0 everywhere. Plugging in 2 pi, this becomes 0, so this becomes 1/2 times 2 pi squared. So this is 2 times pi squared. Okay, so that is the work done by that force. Okay, on that object traversing that circular helix. All right. Okay, so I'll stop there. It's a good stopping point. But this gives you a nice example of how to compute these things. So talk a little bit more about line integrals in this form, and then we'll have some nice named theorems to start rattling off and talking about their applications. All right. So we'll do that starting on Monday. But as I mentioned in my announcement yesterday, later here in a little bit, here in like maybe an hour or so, I'll post your exam 3, which will just contain chapter 14 stuff. Okay, and it will be due on Monday at midnight. So usual format, usual rules, all that stuff. So be looking for it. All right. Okay, so I will see you all on Monday.